Okay, so I guess I should reintroduce this to everybody again. So both Pig, Hive, Cascading, nearly everything out there that does data processing uses an acyclic graph of jobs to do any work. And before we start looking into what Tez actually shows when you run anything, performance issues of Tez, and the improvements we can get with Tez, we should look at how the DAG, as far as Tez is concerned, is organized. So we have a acyclic graph of different parts of the job. Everybody who has seen MapReduce has seen the simplest version of it, which is a map vertex and a reduce vertex connected by a shuffle edge, right? And the shuffle edge in this particular context is sorted. What Tez did was to actually take that particular two-letter alphabet and produce an almost infinite variety of connections you can produce out of that. So which basically meant you could do map reduce reduce and map reduce 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 reduce, or any number of mappers connected to any number of reducers by different sort of edges. And for each task that you end up doing in that, so each vertex consists of a number of tasks, which is the physical distribution of the job, whereas the vertex is a logical concept there. We have multiple attempts for each task to have our failure handling work out correctly. And to actually run this on a Hadoop cluster, we talk to Yarn, ask for a container, grab a container, and reuse that container for any task of this vertex and pretty much any task of this DAG. And if you are using something like a big shell and you have the shell open, the next thing you run will also use the same containers if you have container use across sessions turned on. This is how a DAG looks like, and as you can see, it's got a bunch of mappers talking to a bunch of mappers, talking to reducers, talking to more reducers. This might look very different from the traditional MapReduce system because I think Rohini explained this earlier. In MapReduce, between every one of these stages, you would have a write to HDFS. And a write to HDFS is painful or slow in terms of performance because by definition it has to cross a rack boundary and write to a data location that sits on a different UPS or a different switch from the current data source. Which means that if you have a very large cluster of hundreds of machines split across 4 or 5 racks, you end up stressing out the rack boundary network connectivity, which is the most expensive thing to buy in a large data center, right? So instead of using that full bandwidth to write 3 replicas of data that lives for a few seconds, what we end up doing is we end up connecting them up so that in case a machine fails, we can rerun that part of the tag, right? So we take the optimistic approach saying that as long as most machines don't fail, not writing 3 replicas for every bit of data is going to be faster and more scalable. So this particular DAG view is the most important thing that I use to figure out how a Tez DAG is connected, because as you can see, in the MapReduce case, you could just see what mappers ran and what reducers ran, and that would give you all the information that you need. But the way Hive produces plans or Cascading or Pig produces plans, there are so many connectivity directions. For example, in this particular context, I know that map 6, map 3, map 1 and map 2 have to run before, map 6, map 1 and map 2 have to run before map 3, and reducer 4 can only finish after map 3 finishes. And I'm not sure if you can see this, but some of the edges actually say broadcast instead of sorted, which basically means we don't actually do any of the sorts. So, most important part about performance in a system is observability. So this is the first bit of observability you get into the Tez framework, which is how are things connected logically. You can actually use Graphis, which is a very old AT&T tool from a long time ago, which was used to show network connectivity, to actually visualize this particular graph, and we actually print it out in the format a tool called dot in Graphis takes. Or you could use one of the JavaScript bookmarklets I put up, which gives you a one-click interface to this particular log data. So once you have an idea of where things stand logically, nearly all the information that you want to collect is stored into a system and built into a yarn called ATS. So ATS stands for Application Timeline Service, and it records a sequence of events that come from the different parts of these vertices as we execute them, and we actually store them in sequence. And from that information, we can actually get not only information about a task which has completed, but also a task which is currently running. This includes all the information that you are used to in a MapReduce like framework, like counters, start time, end time, number of attempts of a task, where did each attempt run, where are the logs sitting. So Tez 8 is a branch which contains most of the work that we are doing on the off branch of Tez, where this UI sits today. And this UI reads all data from the Yarn ATS installation and puts it out and gives you a view of what Tez is doing. So this is the landing page you sort of end up in, which is not exactly the same as the application master UI if you're used to Yarn, but it actually splits up each DAG independently. Each DAG that you run is listed out independently rather than being part of each application. So you might notice that I've actually searched for my name there to find out all the DAGs I've run recently. And I get a list of all the DAGs I've run, all the DAGs I've killed. The none failed here, yeah, the none failed here. And the number of seconds each one of those do. So hopefully I'll be able, from this particular view, I'll be able to figure out what is running right now, what did I run before. And as part of the next drill down, I'll be able to go look in one particular query to figure out what did it do. So this next drill down actually shows you how many vertices ran and the parallelism of each vertex. The parallelism of the vertex is how many tasks actually compromise a vertex. In this particular case, you can see that the small broadcast maps only ran one each, and the large join task took 205 tasks to run, and then there are two reducer stages which took 4 tasks and 1 task after that. So logically speaking, it's actually a funnel which has 2 tasks in the beginning, which generate a little bit of data, which is read by 205 tasks, which then produce a funnel which is fed to 4 tasks, which produces even less data, which is fed to 1 task, which actually writes a final output. Now from the earlier DAG and this particular data, we can actually work out how the data, how many machines the data flowed through, or well, how many machines is the wrong, how much parallelism did it have when it ran physically, because obviously one machine runs more than one container. So obviously that is not enough to figure out how much time did each vertex take, right? So if you click through the vertex view of each vertex, you'll end up with a view that tells you when did it exactly start, when did it exactly end, which not only tells you when did it run, right, in this particular job, but absolutely when did it run. If somebody wanted to know when did this particular vertex run on our cluster, in the MapReduce case it's easy because map and reduce run one after the other. Map runs first and reduce runs second. But in the Tez context, you have to figure out which part of the DAG that ran now. And most importantly for me, it tells me how many tasks were successful, how many were failed, and how many were killed. Usually, I like those two numbers to be 0. But if you want to actually drill down deeper, you can actually, while it is running, you can click through the tasks list and you'll see how many of them are successful, how many of them are still running. And if they're running, if you click on the log line, you'll end up getting the runtime logs. So if you're running 205 tasks and one of those tasks hasn't finished yet, you want to figure out why it hasn't finished. You click through this to figure out what that container is doing right now. When the job is entirely complete, if you click on it, you will get a log that is collected by yarn log aggregation and stored in HDFS. And depending on how you configure your log aggregation, it will live for that many days. Ideally, it would help if you set the ATS's time delay of when it deletes data exactly the same as that, so that when ATS throws away old information, so does the log aggregation. And occasionally, we end up freezing a browser if you click view and it loads up, tries to download a 300 or 400 MB file into your browser. So we added a download link on the side just to prevent all the people who had to reboot their laptops because they clicked on a large laptop. The counters are equally useful for in this particular context because we not only collect counters Tez generates, we collect counters that is generated by the application that uses Tez as a framework. So even though this is actually showing Tez counter information today, what you could actually end up having is Hive has input records processed and output records produced, which lets me guess how much filter selectivity I have in a query. Like Daniel earlier mentioned, like you have to figure out how much your filter selectivity is. Right? You can always figure it out by running queries all the time. You'll have to go back to old data, look up to see if predicate pushdown will help you. For that, you'll be able to run something like this and look at how many records were read by a vertex, how many records were written by a vertex, which will give you a good idea of how much selectivity is there, assuming there's no aggregation like a group by involved. Or, as far as performance is concerned, the most significant factor I always look at is how much data was shuffled between machines via memory rather than shuffled to disk, right? So, I can look at how much data went from shuffled data went to memory as part of this. Not only that, because we have more than one shuffle edge per vertex, we actually can split out each edge for shuffle between what is a source task, what is a destination task, so that I can figure out for map 1 how much data was sent to map 3, or for map 3 how much data came from map 1 in this context, and for map 3 how much data came from map 2, and how much data came from map 6. Now, this helps a lot when you look at it at the very granular level, because if you have seen shuffle joins as they're implemented in MapReduce, what it used to do was it would take the left hand side of the table, right hand side of the table, process both in the same map task, and send one shuffle input through. So if you looked at the reducer in MapReduce, you couldn't figure out how much data contribution to a bucket came from the left hand of the table and how much contribution came from the right hand of the table, right? So because we split counter information across edges, you can actually figure out whether map 1 produced more data for map 3 to consume or map 2 produced more data for map 3 to consume. And this is extremely useful when you're trying to reorder your joins so that your joins have the least amount of data flowing through the system, right? You want to figure out that if I did map 1, map 2 and then map 3, less amount data flows than if I did map 2 and, I mean, in this particular context, store sales and customer demographics and item joins we do. We can actually, from this data, I can actually figure out that whatever map 6 sends is the least amount of data that I should probably do last. The next part of this particular thing is, compared to how we used to do things in MapReduce, Tez brings in extra complexity that makes it hard to debug, in particular Hive, because for each vertex you have its independent configuration. So unlike what MapReduce had to do, the configuration is not all or nothing. You can turn on features for certain vertices and turn off features for certain other vertices. The best example for it would be the auto reducer parallelism we have. For example, if you're doing a group by, it doesn't matter whether the destination has 200 reducers or 100. But if you're doing an order by, it really clearly matters that you cannot reassign them arbitrarily, right? You're expecting 15 buckets as your output, you want to run 15 reducers. So, as part of the entire query plan, you can figure out whether the group by vertex has one configuration like auto reducer parallelism enabled, and whether the next one, which is an order by, doesn't have it. You can actually go through each vertex and check whether the configuration plan for each of those vertex is what you expect. This gets even better in some sense because you don't have to send the entire plan to all queries, all parts of the system. So if you had a query plan and configuration setup which didn't fit in, which doesn't have to fit in all parts of the all containers you allocate, you can allocate a 10 GB container for one vertex in the whole pipeline and use like 4 GB vertices for all 4 GB tasks for all of the rest of it. And this particular view of each vertex, and I don't know how many of you recognize that I'm running word count here, will tell you which configuration is enabled for what. And in particular, when you're trying to debug, say, security issues like Kerberos, key tab, which key tab is it using right now, this is like incredibly helpful. The last part, performance is good. We want all queries to work. And when queries fail is when you need all this information as clearly presented as possible. So if a query has, if a DAG has failed, the first thing you would see when you hit the DAG page would be what is the last error you got, right? Like this is basically saying that we got a Hive exception on this particular row, right? And that it will give you a list of failed tasks, right? It will not only tell you that it failed, it will directly link you to which task among all the tasks you had failed. Not only that, if you went through the whole process, it will tell you which task failed in which attempt, how many attempts ran, which machines did they run, because most of the time, occasionally, one bad machine will be responsible for every single failed task you have had in your entire cluster's life. And being able to narrow down that machine just by clicking through a bunch of things saves me a lot of time instead of grabbing through logs and sort WC, get L, unique C, which is what we used to do before. So this is the stuff that we have as part of Tez 8 that is sitting in the branch in Tez. And that gives you an overall view that is usable every day, all the time you run a query. You want to see nearly all of that information. But sometimes you'll end up with scenarios where you have something that is working slowly than you expected, or not working the way you would like it to work. And we have developed at least a few ad hoc, post hoc scripts and tools which let you get some information out for some special cases. So, swim lanes is one of the few things that I use very heavily. This particular chart is a very simple two mapper, 12 reducers, I think. MR pair, which is being run. In this context, you can see that the green lines start where the containers actually start their lifetime, and there are red lines, which I probably cut off at the end, where the containers are actually killed, right? And you can see that two maps ran, and in this context, the red underlines means that I didn't get a container where I asked for it. And with this particular view, I can tell which task among all the tasks that ran contributed the most to my delay, and which tasks were not allocated where I wanted them. So the swim lane graph is actually drawn from the application master logs we have. So we actually go grab all the logs, grab through them and draw this line, which tells you how much container reuse is happening. You can say that one of the reducer 2 is actually getting scheduled in the same container as the map task, because each horizontal line is one container. And that the entire DAG took like 2.5 seconds to spin up the first container. This particular timeline drawing gives me a lot of information to analyze a slow query or a slow job post hoc. And on top of it, because we discovered that log processing was a big data problem that Hadoop really excels at, we wrote a T-file parser. I don't know how many of you people are aware of what a T-file is. Hopefully not a lot, but this T-file is the format we currently store the yarn logs aggregated in. And it is aggregated and stored as compressed text in a key value store format on HDFS. And obviously, we turn to the standard tool we use to process it, pig. We load the data up using a T-file storage into a big row line. I shouldn't call it the row format, it was originally just reading lines. But now we extract out which machine it came from, what file is it, for example, the standard error versus standard out versus syslog, and what the actual data line is. I've linked a UDF Groovy script which is used for pig, which actually reads the log4j format, which tells you what time did each line get written from the timestamp, whether it is info, whether it is debug, and what the actual content of the data is. Now this by itself was written because I got about 72 GB of logs. I got 72 GB of logs in T-file format, and Rajesh, who works on Perf team as well, Rajesh wrote this big T-file storage to load it so that we could analyze it, because we didn't know what we were looking for at the beginning. And slowly we started to figure out what we were looking for, and we were looking for one particular issue where we were trying to find a bad machine. So this graph that you're seeing here is drawn using GNU plot, and the data, CSV data that we mined out of pig, and it contains the amount of time it took to transfer data from a source machine and a destination machine, with the actual color and the height representing how much time it took. And from this data, we found out that one machine was causing all the delays in the cluster. Every single delay in this cluster was because of one machine, and if you just threw that out, every job became faster, right? So after succeeding on 20 nodes, which is a 20 node case, we decided to just go all in and take run this from the data from the 350 node cluster, which had 350 data points in the x-axis, 350 data points in the y-axis, and 100 data points for each pixel you're going to see, right? Because it has 10 containers per node, talking to 10 containers on every other node. And we found out something we would have never seen without this particular tool. We found out that, obviously, big data problems have to be solved with big data solution. GNUplot took about an hour to render this because of the number of points we had, but it very clearly shows that one rack in this cluster has very bad connectivity to the entire rack, which is the line that you see moving from left to right. And that one machine in the cluster is serving out that data very badly, which is the line that you see inward. And there were two machines which were very bad at talking to themselves, right? The eye of Sauron that you see at the top, right? So once we started treating the log files we generate from Tez as input for pig that runs on top of Tez, we started to find that mining big data has huge advantages when it comes to understanding what we do in clusters. So take out 3 machines from this cluster and 1 rack. The throughput of this cluster will actually go up rather than down. Now, this kind of analysis is possible today because we first of all log an info level for this particular data. On top of it, we can actually mine the data we generate from Tez using pig. And we earlier talked about using ATS, the application timeline service, to store data. For clusters, we don't have application timeline service. Tez logs all the counters it has as a Hive table, which you can query as a Hive table if you want to, right? So we are literally like dogfooding the whole process. We are using pig on Tez to process data that was generated by pig on Tez, so that we can figure out how to fix the first pig on Tez or the second, I don't know, both. The data at the bottom, the line that you can see, the shadow that you can see at the bottom, are all the tasks whose data was obsoleted, which basically meant that when other people tried to fetch data from that machine, we had connection errors and we had to throw out that data and rerun it, right? So even though the UI layer stands as a generic tool to figure out what is wrong in the system, when we do not know what we're looking for, we turn back to the same tools we used to look at data that comes from everybody else to find out what is wrong with our own systems. That's pretty much all I have. I would like to thank all the Tez people who contributed to all this. I didn't write any of the UI code. I only complained about it until I got what I wanted. And the Hadoop Summit, the call for papers is out. So, questions?
Are you contributing the T-file loader?
It's actually checked into the Tez tools directly right now. Hopefully we'll get it into Yarn directly. But having Yarn depend on Twig is kind of complicated to do, rather than leaving it there for anybody to use. Because the same T-file loader can be used to analyze MapReduce logs as well, or anything that runs on Yarn. Storm, anything you want to talk about, we can use it. Yeah.
So at what point during the point of debugging and doing performance analysis would, say, a developer or a DevOps person would say, okay, I can't really figure out what's going on with the UI in Tez.
Yes.
I need to resort to this three-dimensional graph.
You would have to be somebody who's trying to figure out on a very large cluster where you cannot download the entire data or logs to your local machine, right? So it is 700 GB of compressed data. Grabbing through it would take multiple days. Anybody running large systems would need some sort of similar solution to do ad hoc data processing. So we didn't start out to build that UI. The first Tez UI you saw, we did start out to build that UI to serve people. The rest of the stuff came because we had the processing tool. We had some data we wanted to show or find out, and we couldn't bridge it until we built all these little bits. Right? The T-file parser took 2 days to write, but if you ask me today to write it like now so that we can debug something, I probably wouldn't. So these are things we have kept and built so that people who use Tez do not have to build them again. Right? But the initial part is meant for people who want to use Tez on a daily basis, want to figure out what is happening. And for the rest is for people who want to understand how to look for things and they don't know what they're looking for. Like we didn't, like this particular graph, we had no idea what we were looking for. We were trying to figure out whether there are any machines which are causing issues, and trying to explain to people like which machine is causing issues using Excel sheets didn't work. And the visualization work comes in later because you want to explain to people as clearly as possible. Like this is data compression in terms of like information compression. Right? And human beings are really good at seeing things. They're not good at reading numbers.
So one indication would be the number of tasks in the UI where you actually see all the tasks have succeeded, some have failed, and some are still in the direction. If something is actually taking exceedingly long, then it's an indication of something.
Yes.
Something is going wrong.
Yes. Yes. You would see that like some machines constantly show up as running slow, and this is like a formalization of finding that. Yeah. The mic is.
I'll just talk.
Yeah.
I know this isn't the point of your talk, and you may have just said it because I didn't hear the question. But what was wrong with those two systems?
I have no idea. I have got the logs. The best I can say is I told people put them in Yarn execute. Do not schedule anything.
Got it.
Right. Fixing stuff is, finding stuff is the problem here. But I don't know what. Maybe they were bad disks. Usually, it's always bad disks.
All right. Let's go give a